Gaia black hole 3, am I right? We've been talking about it for, I think, since as long as the program has been going on. I'll be talking about the formation of it. And hopefully this is a talk, but this is also an open discussion. I am giving an answer, and I'm hoping that someone will find a hole in the argument, a plot hole. But yeah, let me first start as in, who doesn't? As in, how would basically an alien understand this conference? Basically, the idea is how do we detect black holes? And we've presented many views, many different approaches. I'll be very general here because I'm talking with all the experts in, or most of the experts in all the fields. So yeah, I'll be separating them into distinct categories, and you'll see my background here. I'll be separating them in gravitational waves and other. So yeah, gravitational waves, black holes merge. We detect their last second before they merge into two black holes merge into one, and that produces deformations in space-time that we can detect with LIGO, Virgo, Cagra. Electromagnetically, well, lots of families. We have astrometry. Johanna's talk, I really liked your figure about how we detect black holes electromagnetically, spectroscopy, photometry, X-ray, well, etc., etc. The thing is that these uncover what are the black holes that we see using these methods. In gravitational waves, we see generally large masses with a median mass of 30 solar masses, and black holes that are outside of the Milky Way. In electromagnetically, we see in general stuff that's in the Milky Way and generally has lower masses. Let's say, and this was when I looked only at X-ray, but the idea is, I think, holds. For confirmed masses, it's below roughly 10-ish solar masses in general. What we're seeing here is that basically we are looking at two different populations. So two methods detect two different populations. And that's obvious, actually, if you come to think of it, especially gravitational waves, because it introduced lots of, like, you only see black holes that are just 1 second into crashing into each other, really tight orbits. Now, do we have any black hole that kind of bridges both of these populations? The answer is yes, obviously. That's Gaia black hole 3. We've heard about it a lot. I'll just briefly mention all the properties again. It's a dormant star black hole binary, and I think this plot has also appeared even today. Black hole binary doesn't accrete, very wide orbit, period 4,000 days of a giant star, less than 1 solar mass, and a black hole that's 33 solar masses, eccentricity of 0.7. The star is extremely low metallicity, and this is key point located in the ED2 stream, stellar stream. I'll talk about this later. The fact is that the black hole sits very nicely in the middle of the mass distribution of black holes in gravitational wave detections. And I think, yeah, I have this plot that basically shows this is a cumulative distribution function of detections, not the underlying population, but detections of black holes using X-rays and gravitational waves. As you can see here, these represent two different populations in mass, with sources detected with gravitational waves being more massive, and Gaia black hole 3 sitting almost right in the median. So yeah, we see an object that's in the Milky Way, but has the mass that's detectable, that's comparable to those detectables with gravitational waves. So understanding how this binary form can put constraints on how binary black hole mergers form. And I think this is why I studied this object, this is why I care about this object, and I think this is the way forward to do multi-messenger astronomy or multi-messenger population. And this is also related to Smadar, what Smadar was saying. We should combine all the populations or all the models or all the predictions possible observables, and try to disentangle the formation physics from there. But in this case, I'll talk about clusters. So Gaia black hole 3, we've said it, it's kinematically and chemically associated with the stellar stream. This plot, this will appear later again. This is a plot that I got from Eduardo Balbinot. This is galactocentric coordinates, and you can see here all the stars in the stream and their velocities, all positions X, Y, Z, and Gaia black hole 3 being basically in the middle of the stream. And this is what prompted me, or what gave me the idea that this could have been formed dynamically in a cluster, and the cluster dissolved and formed a stream. Now, the first analysis that we did, also with Kyle Kremer, that's around here, basically we got a set of cluster models, and we checked what these cluster models were, or what kind of dormant star black hole systems these cluster models were forming. Basically, what I did was just extracting them, putting them in this triangle corner plot, and seeing their properties. So these are all the properties, the masses, the mass of the black hole, the mass of the star, the eccentricities, and the periods for all dormant star black hole systems. And basically, the colored areas are what we see, and the red star here represents Gaia black hole 3. So, takeaway from the first paper is that clusters produce objects that are similar to Gaia black hole 3. So yeah, mass, period, and eccentricity are compatible with a cluster formation scenario. But this doesn't imply the other way around. Maybe while clusters can form this object, maybe Gaia black hole 3 could have formed in isolation. So the goal of what I'll be talking about today in my current paper is proving or showing that Gaia black hole 3 did indeed form in a cluster, and there's no other way to have formed this object. Now, the way we do it, because we're cluster modelers, we model a cluster. So what we did was model the progenitor cluster of the ED2 stream. The ED2 stream is formed from a now dissolved globular cluster. So we got that cluster, and we did a targeted simulation of what we believe the initial properties of the system are. We ran 90 cluster simulations, and we varied. All these are, of course, n-body simulations, fully accurate with galactic potential, stellar and binary evolution, etc., etc. We followed the orbit of Gaia black hole 3. So, and we let the cluster evolve, and the cluster is as old as or at least older than 10 gigayears. So we let it evolve in the galactic potential. We used the same metallicity as the star. We get some constraints from the mass of the stream of what the initial mass of the cluster should be. We have a lower and upper limit. The lower limit is very obvious. The stream or the globular cluster should at least have formed a black hole. That's obvious. The upper limit is derived from some chemical abundances, which I'm definitely not an expert of, but there's an upper limit on the mass of the cluster. And the way to do it was we tested scenarios of early and late cluster dissolution, and also scenarios where the cluster formed with many binaries, a 40% binary fraction, or without primordial binaries. Also, we ran an extra set of models of a cluster that dissolved really early and had a really low initial density. Why? Because this is actually something it came up in a presentation some time ago when I was presenting the first paper. It was like, okay, maybe Gaia black hole 3 formed in a cluster, but the cluster was extremely low density, and really dynamics did not have an effect on that. So we tested the possibility that indeed the cluster was initially had a very low density. And spoiler alert, these models will not reproduce the stream. So the first what we did, of course, we ran these simulations, and we compared the stream, or the visible part of the stream of the simulations, with the actual Gaia data. This is the same plot I showed before. In blue is my simulation, and in black is the ED2 data derived from Gaia, from Gaia data. As we see here, we find the qualitative match of the stream. Of course, we will never find an exact match of the stream because this has evolved in the galaxy for more than 10 gigayears, and the positions and velocities are all kind of a stochastic process, etc. We'll never find an exact match. It's not what we aim for. If we find an exact match, we've done something wrong. But the thing is that we reproduce this stream. So our cluster simulations are actually simulating the ED2 progenitor cluster. Now, this is very qualitative, but we can also go a bit further. We can bring this to a quantitative match. Then what I did was get the number of visible members of the stream. Of course, not all members of the stream are visible. Since the clusters evolved for so long, some stars are on the other side of the galaxy, and we really do not see them or would not associate them with the stream. So applying the same cuts as we would as they applied in identifying the stream, we identify the number of visible stars in the stream, and for all of our models. So what we find is that this low density model that I showed before at the beginning has a very sparse stream, a stream that's very dissolved in the galaxy and really does not match or cannot reproduce the structure of the stream. It's very empty. Instead, our models prefer or argue for actually more massive clusters and more higher densities. So by comparing our models to the stream, what we find is that actually the progenitor cluster of the ED2 stream actually had relatively higher masses within the mass range, and most importantly, higher densities, which means that dynamics, or I will later introduce it, that dynamics really does have an effect, and dynamics cannot be avoided in the formation of Gaia black hole 3. Now, there's some caveat here, and the caveat is that maybe Gaia black hole 3 is not the exact same center of the stream. Maybe Gaia black hole 3 is just in some part of the stream, and maybe we're just seeing it in the center of the stream, but that's basically an observational bias. Maybe we're just seeing some part of the tail of the stream. So the way to fight against this potential caveat is to just evolve the stream a bit and assume that we're not seeing the center of the stream. Basically, if we take what we observe now as the center, or the position of Gaia black hole 3 as the center of the stream, we evolve it forwards and backwards for 100 mega years. And we get this result. It's basically the same thing. We still discard these low density models, and we prefer, from our mass range, we prefer the higher mass models. All right, and we haven't even looked at the dormant star black hole systems. So we know that Gaia black hole 3 formed in this higher density cluster that then dissolved and formed the ED2 stream. But within the cluster, how did it form? And I'm proposing here 4 formation scenarios. The first one will be that it's just a primordial binary, that you put a binary in the cluster, it evolved with some interactions, and that's it. That's Gaia black hole 3. I'm proposing the scenario of an exchange, whether the black hole was formed in a binary with a star and then exchange its companion star. I'm labeling here with an interaction. I'm labeling it with numbers so it's a bit more visible, but the idea is that. Alternatively, it could have formed as a 3-body binary or dynamical binary. I'm using both of these terms exchangeably. I think we haven't decided which of these terms is actually better. Basically, at least 3 objects, so black hole, star, and another object, come into a closed area in the center of the cluster, and 2 of them form a binary. You need at least 3 objects because of conservation of momentum, but it's usually a ton of them, and it's always a mess. But yeah, it can be found in our simulations. And I'm also proposing a fourth channel, and this is the one, I'm leaving it here, so if you want to take a picture of the screen, the quasi-isolated channel, meaning that the binary may have formed as a part of the cluster formation process, but really did not have any interaction. Basically, what you put in is what you get. I'll be testing these 4 scenarios with my simulations and giving numbers for the likelihood of any of these 4 scenarios. Now, how do we test this with a cluster simulation? Because a cluster simulation, everything is coupled with everything. So how do we do it? Basically, we have some clustered models with binaries and some cluster models without binaries. The clusters with binaries will form these 2 objects, which we then can identify based on their whether they were part of a binary formation or not, and clusters without binaries that can form these 3-body binaries. For the quasi-isolated channel, what we'll do is a bit different. We'll get these binaries from the clusters with binaries, and we will evolve them in isolation. So no effect of the cluster. And we will see whether the dynamics of the cluster had any effect on the properties of the binaries. Spoiler alert, it will. So this is for the first 3 channels. This is what we find. This is the average number of star black hole systems per cluster as a function of the period, eccentricity, and mass ratio for the primordial, exchange, and dynamical channels. And also as a line, Gaia black hole 3. You can see here that basically what fits best the parameters is a 3-body formation scenario. This is also what Sarah, I think, will say in her talk. But also, the dynamical formation channel is not very efficient. So when you have something that fits better the parameters, but fits slightly better the parameters, but the rate is very low, you do Bayesian inference, which, yeah, we know what it is. So I did Bayesian inference to get the most likely formation scenario based on the rates and based on the properties. And what I find is these numbers. So with the 78% probability, Gaia black hole 74, sorry, Gaia black hole 3 form as an exchange binary. So we have that Gaia black hole 3 form as a black hole, as a binary of stars, one of stars converted into a black hole, and exchange its companion star. And that gave rise to all the properties observed now of Gaia black hole 3. Yeah, also some 23% probability of the primordial channel, and the dynamical channel is extremely low probability just because of the extremely low rate. Now let's compare to the quasi-isolated channel. The possibility that the binaries did not change because of interactions. Here I'm showing in red, I think it is, the properties of the quasi-isolated channel. And as you see here, they really change a lot compared to the primordial binaries. So really interactions, you cannot avoid interactions in the cluster. You cannot avoid having interactions that change the properties of star black hole systems. Now, not only the properties change, but also 40% of star black hole systems are, or potential star black hole systems are disrupted because of dynamics. So really, 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 there's no way to escape dynamics. And I'm driving this point even further with the cumulative distribution function of the number of strong interactions. So as a median, each star black hole system that we find in our simulations has 84 binary single interactions and 9 binary interactions, so really unavoidable. So basically, as a consequence, there's no way to predict, to have any other formation scenario for Gaia black hole 3 that does not involve cluster dynamics. Now on to alternative formation scenarios, as I said, or alternative, not formation scenarios, but interpretations of the data. I've been heard, or I've been proposed the idea that Gaia black hole 3 maybe could have been a hidden triple. So the inner black hole, maybe it's two black holes, and then the outer star is just the outer star. Is Gaia Black Hole 3 actually a hidden triple? Basically, in our simulations, no, it isn't. It just saw any triple involving an inner binary black hole is extremely wide. It's extremely, the same measure axis is orders of magnitude larger than Gaia Black Hole 3. So really has nothing to do. So we completely discard this formation scenario. Also, as maybe as a curiosity, but I think it's interesting, the distribution of formation times of these objects. For exchanges, they form relatively early on, while for these dynamical formation scenarios, we see most of a constant distribution of formation times. We could argue about what this means, but one thing that I find here is that there's no formation after 8 gigayears, which means that it did not really form in the stream, because this is also some idea that has been proposed, formation in the stream. That's not really possible either. So onto the future, what will we detect for, or what do we expect for future Gaia data releases or future surveys? Basically, for cluster dynamics, we see that the efficiency is lower for higher cluster masses or higher for lower cluster masses. So per unit of initial cluster mass, lower mass clusters are more efficient at forming these objects. So we should be looking at smaller clusters, because they're more efficient. There's more of them, they dissolve, they form Gaia black holes, they dissolved, and this is what we will see. Of course, if you put binaries in the cluster, they form more star black hole systems. That's something that basically everyone expected, but also because of the lower rate of three-body binary formation. And now this is our stick next out prediction. We say that there's order of 1 Gaia black hole 3 in the U2 stream. That's fair, that's safe. There's 10 to the 5 of these objects in the Milky Way formed from clusters, and there are about 100 of these objects within 3 kiloparsecs. This is the key point, 100 of these objects within 3 kiloparsecs. So this is roughly what we would be seeing. No, dormant star black hole binaries forming clusters. Any mass, yeah. Yeah. This was before Gaia mock, actually, but yeah, we predict about 100 of these objects. Now, finally, yeah, as a conclusion, I'll be short here. Basically, the ED2 stream formed from a now dissolved low metallicity globular cluster with a high initial density, and that system formed Gaia black hole 3 via interactions. Most likely, Gaia black hole 3 was formed in a binary that then exchanged its companion star and underwent, obviously, multiple strong interactions that really affected their orbital properties. And we predict 100 star black hole systems within 3 kiloparsecs. And yeah, this is my key point. If you want to study dormant star black hole systems, you can never disentangle it from cluster dynamics, the population in total. Thanks. Okay.
I've got to go to somebody that didn't ask questions yet.
Hi, Savannah Carey. So I was wondering if either in this study or maybe future studies, you've considered fractalization in your clusters, especially when you get to these lower mass clusters, right? They're not going to necessarily form in these perfect plumber spheres, which can, create these localized pockets of, density over densities, and maybe disrupt the cluster sooner rather than later, affect how the stream looks, et cetera, et cetera.
Yeah. This is relatively, okay, I understand this may be a bit of a circular argument, but our models predict that we tend to get from the available available mass range, we tend to go to the highest, so that's 10 to the, let me check with the, sorry. The highest mass is 4 10 to the 4 solar masses, so fractal initial conditions may have some effect, but they would just increase, the pockets would just increase the effect of dynamics. So the conclusion still stands.
Okay, yeah, maybe I missed this, but how do you model the formation of the stream? Or like, what's the mechanism that's responsible for the cluster dissolution?
The tidal forces of the galaxy. We use
the present-day galaxy.
Yes, that's our other caveat. We evolve them using a very simplified model of the galactic potential, which is definitely not going to be correct for the last
formation epoch of the cluster.
Sorry?
Potentially not correct for the formation epoch of the cluster from which the system originated.
Exactly. That's why we're not actually matching the exact shape of the stream. We're just matching roughly the number of visible members.
But I think it's not only about matching the properties of the stream, but this would obviously also affect the time at which you can dissolve the cluster if you have a different potential or another mechanism that can play a role in cluster disruption. So this can influence the impact of dynamics.
There's two things there. The dynamics that form these objects actually happen in the center of the cluster, so they're not really affected by the potential of the Milky Way because it's just the effect of the, let's say, the tidal forces are more important at the outskirts, and this is a process that happens in the center. That's true that the actual dissolution time is going to be complicated to compute. That's why I don't say, yeah, the cluster dissolves at exactly 7 gigayears or 8 gigayears or whatever. I'm just saying that if we evolve it in a Milky Way-like potential, it does this. It's obviously not, it's the best we can do with what we have.
I let others.
Great talk, Daniel. I was wondering if you looked at all, like what fraction of these end up in something like a stream versus maybe get kicked out at higher speeds and don't end up in like the cold part of the ejecta distribution?
No, I haven't checked that. The thing is that, yeah, okay, I see your point, whether it stays on the center of the stream or whether it's ejected from there. No, I haven't checked that. It could be interesting. The thing is that it's so, at this point, the simulations are, if you try to do some stuff like that, they become a bit low number statistics, just because the efficiency of the formation of these objects. You produce a handful of these objects per cluster. So some of these analyses, you have to be very careful on what you do, because at some point, we try to check the detectability of these systems. That's also a question that may come up. The problem is that since we don't know exactly where in the orbit the stream is, that's why we do the plus minus 100 megayears. We're running on low number statistics here. Yeah. So number of star black hole systems per cluster, it toys around 1 to 4, a handful. So yeah, low number.
So, sorry, I have the microphone. I have a question actually on this plot, because on the left for the low mass open clusters, you're clearly seeing, especially for high binary fraction, essentially a uniform efficiency, or even a slightly increasing efficiency. But we know as I go up to globular clusters on the right from your other paper that there's a stark decrease in efficiency with mass. Can you just talk a little bit on what drives that and where you expect the turnover to be in this?
That's gonna be, that's something that for a future project, for sure. But there's the effect that these clusters do not have the same initial densities. So this is a set of simulations, and this is another set of simulations. and they don't have the same initial densities. So I think we may be comparing apples to oranges here. That's also something that I learned that's relevant for comparing sets of simulations of black hole mergers. We are hiding something here, and what we're hiding is the initial central density, and that may play an effect on seeing. Actually, maybe just smooth, and what we're seeing is just two different sets of initial.
I have a comment and a question.
Yeah.
So the comment is that if Gaia BH3 had two black holes before that, the recoil kick can change the parameters after the behavior. So that's not a problem at all. Even more so, your exchange interactions have always the tertiary stays for a little bit before it being kicked out. So naturally, you create actually the exact same conditions that I described in my talk. So that's the comment. The question that I have actually relate to several questions that were asked here. The system, as it moves within the galaxy, undergoes a change, a dynamical change of like an experiences of a changing potential, and that will affect your dynamics. You say dynamics is really important. We cannot get away with it. I will double down on this and say yes. And I would encourage you to take into account the changing dynamics. So my question is, did you have an external potential that changed it as a function of time in your simulations of the clusters?
No. So two things. First, on your comment, I agree on what you say. The problem is that we're still don't have accurate prescriptions for the kicks in gravitational wave kicks here. I'm just saying whether not that it formed in a triple. Actually, it was triple at some point because of the interaction, but it's not a hidden triple right now. Yeah, and I did not consider a moving or a changing potential just because it's not available. So it would have to be
an external potential that you can add that is changing, and that will induce a quadrupole all the time on your.
Yeah.
That will induce a quadrupole moment on your dynamics. That will be more interesting and make probably things more efficient.
Yeah, but that would affect mostly the outer region. Right?
I don't think so.
No? Okay.
So in these clusters, does mass segregation not happen that prevents low mass stars from interacting with these massive black holes? And in the exchange encounters, is it not more likely for the lower mass star to be ejected out of the binary?
Yes, mass segregation happens. The problem, I have to look into this more carefully, but the general idea is that this happens at so black holes are in the center, they form binary black holes. Then you have a regime when there's black holes and stars. So this is where these processes can happen. Also, yeah, you're right. The most likely scenario is that the low mass star is ejected, but that's a likelihood game, and this is why we're seeing these very low efficiencies.
Couple of information and very quick questions. So here, for example, when you mention numbers expected, are they like Gaia, like with a 30 solar mass? It's the general. Okay, thank you. Then I have a real question. Okay, if you go to your 4 scenario panel, the most likely you say, yeah, here, exchange. The binary before the exchange could be formed through dynamical. You don't need it to be primordial binary, right? So the 2-3 pair there, is it a primordial binary?
It's a primordial binary.
It is.
Yes. Well, the way to define it, if you want to go to the muddy technical stuff, is that the black hole was part of the binary at some point, and then the black hole was in a binary with the star.
Okay, so I'm having so the reason I'm asking is because here, for example, Is the black hole already in the binary?
Here.
Yes. So then you're keeping something that you have a very light companion right now in a very wide orbit. So if you're going to kick out star 3, statistically, you're kicking out something even lighter. So the original binary was a very low initial mass ratio binary, if it was a primordial binary. So then ultimately we can have a discussion. I'm very interested in what kind of mass ratio have you given to this cluster before, mass ratio distributions initially for the original binaries? Because, you know, these are extreme properties. And then
I have your answer here. Wait.
And what dispersion, what velocity dispersions do these clusters have? And what is the relaxation timescale? So all of these, in my mind, to make sense of this, these are the kinds of questions I would have. We can have a discussion. My real question is your corner plot.
Okay. Real question. Okay, fair.
If this is one of your best models,
No,
I see.
This is not my. This is from the previous paper.
Oh.
This is not a targeted search of the EV2 stream progenitor. These are just globular clusters.
Okay, so if I can ask my question, maybe in the two-dimensional, many of the properties are in the low density regime.
Yes.
Have you calculated if we can see black hole 3 when the properties are in the wings of this logarithmic probability density, how many more Gaia should have seen black hole and wide? Because the properties are in the wings except for the top panel. So that would be a calculation to do.
Yes, that's interesting, but the point is that there's lots of observational biases here. For example, look at the periods. We're not seeing something that one day. Yes. This, when I did this, this was before Gaia mock. So it's something to consider in the future. Yeah.
Mode goal. My question is a little bit on kind of the constraints you can get maybe from the chemodynamical analysis of the other stream stars. Are you able to take any of that information to constrain your simulations? For example, like how many star formation history as a function of the enrichment you see and the other metal poor stars in your stream?
No, we don't use that. Sorry, we just fix a population, single population that I know may not be the most accurate thing, but that's simplified model, of course, that's my simplifying assumption. All starts with the metallicity of the companion of Gaia Black Hole 3, single population, and we don't look into more.
No, Langer, very interesting stuff. My question is in a similar angle. So I think most of the Milky Way globular clusters show evidence from the chemical distribution of the stars. You know, there's a bimodality, so maybe these clusters have formed in two events or so. I think that's not converged yet, but I see many different cluster formation models in the literature.
Yeah.
Would any of this play a role for your interpretation?
I mean, other than determining the initial binary fraction and the initial mass density distribution, let's say, I don't think it would affect the dynamics a lot.
If you have two populations which form in a time difference of 10 to the 8 years or so.
Yeah, I don't think it really plays an effect there in the overall dynamics of. This is not a model of cluster formation. It's way beyond what I can do with these models, studying the actual cluster formation.
Oh, yeah, thanks for the talk. My question is really like, is it weird? Why have we detected such a massive black hole with Gaia already? Because with gravitational wave sources, like we have a huge selection effect towards massive black holes, but over 90% of the merging black holes in the universe are 10 solar masses, right? So it's actually a very small fraction of merging black holes at 30 solar masses. So is it weird that the Gaia black hole mass distribution seems so much more skewed towards higher masses, even though it's like Milky Way, maybe not as skewed towards lower metallicity? Or is there something about this formation channel in general that would make it way more massive black holes?
I mean, more massive black holes are more likely to be detected in Gaia. Hope I'm saying that.
Yeah, I thought it was a very small selection in mass. I thought it was mostly period.
I mean, Johanna said there was a Gaia BH3 is a message from the future, right? This is actually was pulled out of Gaia DR4 early because it was so exceptional.
Yes.
So I think.
Yeah, by all metrics, it's weird.
Two questions. I think you started to address the first. Do you have a metallicity distribution for those in the stream that are associated with BH3 at all?
No, I use a single metallicity for the whole population.
Okay. Then the second question is Gaia, are the Gaia folks that are looking at Gaia data looking at other streams for such systems?
I have no idea. That's private collaboration thing, probably.
Yeah, it could be. I just asked the question. Maybe something private could be made public.
I don't know.
But it would be interesting to look at other such streams in the galaxy to see whether that's an interesting environment for interesting black hole binaries.
I'm not looking into that. I don't know if someone's actively looking into that.
All right.
If someone wants to spoil themselves.
I mean, people have been looking in clusters, not disrupted, right, for a long time. Isn't that the same thing?
After the discovery
of BH3. So I was wondering if this can help solve the puzzle of why it seems like these are overrepresented at low metallicity, even given this, like, blast from the future, but probably we won't get 10 to the 4 black holes in DR4, so it'd still be overrepresented. And the idea I had is that you showed these, it takes of order a few gig years. I think the median time to form one of these was a few gig years.
Yeah.
So you have clusters at all metallicities, low mass clusters, but most of the ones that are at solar metallicity get disrupted in 100 million years or something like that. So you wouldn't have time for this channel to work efficiently. I don't know. Do you think that's promising?
Okay, what I haven't wait, I think you're referring to this plot. I haven't shown here the primordial binaries. Of course, because they all form at 0 time.
Yeah,
so,
but we don't care about this because we're talking about one.
About the actual, I mean, even
assuming it doesn't work for primordial formation.
Okay, even for primordial formation, you still get some dynamics. Even if the cluster dissolves, you may have you cannot still say a primordial binary evolved in isolation in a cluster. No, it underwent dynamical interactions, and that may have an effect. Yeah, maybe for those high metallicity star black hole binaries, maybe they don't have an effect of exchanges and 3-body binary formation in those clusters. So that may help alleviate the tension. I still would, like to check out or do a more thorough, let's say, analysis of low metallicity star black hole system formation in clusters.
Thanks.
So given your other answers, why do you stop at BH3? Like, would BH1 and 2 also have formed in clusters?
They're not visibly in a stream.
I know, but you said they could have dissolved. I don't know.
Yeah, that's Sarah. They're looking at the formation of these Gaia black hole 1 and 2 in clusters. I just focused on this object because it interested me. The most likely formation places for black hole 1 and 2 are, I don't know if 2, but at least one of them is lower mass clusters. and younger. So this is a completely different population of clusters, actually. So yeah, I haven't done a thorough analysis on all the three. It's just odd object from the future. Let's see where it came from.
Okay, this is kind of a follow-up to Vicky's question. At the time of formation, would Gaia Black Hole 3 have been a hard binary or a soft binary in the cluster that it was in?
Have to check that out. It's on my to-do list. Yeah.
Ilya, do you want the last question?
I think it's roughly, wait, I did check at some point. This is very preliminary analysis from what I remember. I think it's roughly hardish. Let's say not extremely hard, not extremely soft. It's just in the half soft boundary. But I need to actually do that properly to say it confidently. But if you want to take it around. Yeah.
Just following up on Karim's point, if we posit as you have done, the dynamical formation in general, or at least dynamical interactions, are important for forming detached black hole binaries, not just Gaia BH3, right? Then there is another effect, as you've described, right, which is that if you have multiple dynamic interactions, the more massive things stay around, and so that sort of is another way of favoring more massive black holes being found in these kinds of binaries than in the black hole population at large. It may not be as significant as the effect that Karim mentioned, but it's another boost in that direction.
That sounds like a positive enough note to conclude this session and go get coffee. Let's thank Danny again.